Welcome to This Explainer. So picture this. You've written a Python script. It started out brilliantly simple, right? But then, suddenly, it turns into this absolute tangled mess of functions, nested if statements, and just wild, untraceable variables. We've all been there. If you've hit that exact wall, you are in the perfect place. Today, we're taking that messy functional code and transforming it into beautifully organized object-oriented programming, or OOP. And we aren't just going to talk theory here. By the end of this, you'll see exactly how it's used to architect a fully functional high-low game. All right, let's just dive right in. Here is our roadmap for today. We'll start by breaking down classes and objects. Then we'll hit the core pillars: encapsulation, inheritance, and finally, polymorphism and abstraction. After that, we put it all together by building the high-low game. Let's kick things off with Section 1, Classes and Objects Explained. Think of a class as a factory blueprint. It's not a physical thing you can actually touch or drive around. It's just the design. It says, hey, a car should have a color, a brand, and the ability to drive. The object, on the other hand, is the actual physical car you drive off the lot. It's the red Tesla. It's the blue Ford. The real beauty here is you write just one class, but from that single blueprint, you can manufacture literally thousands of unique objects. It is the ultimate tool for code reusability. Moving right along to Section 2, Pillar 1, Encapsulation. The word itself actually gives it away. Think of a standard medical capsule. The medicine, the active formula, is sealed safely inside. In OOP, encapsulation is that practice of bundling your data, like your variables, and your methods, your functions, into a single secure unit. By doing this, you are actively protecting the internal state of your object from outside interference. Look at it this way. How do we stop people, or even other random parts of our own program, from just reaching in and stealing from a digital wallet? In the real world, you absolutely wouldn't let a cashier just reach into your pocket and grab cash out of your pants, right? No way. You are the only one who accesses your private wallet, and you hand the money over through a specific controlled action. Well, our code needs to behave exactly the same way. Python enforces this privacy so elegantly. To lock away your data, you just use a double underscore right before the variable name. So underscore 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 basepan or underscore underscore balance. If some user outside the class tries to type out myaccount.balance equals $1 million, Python will literally just throw an error. That data is completely private. It can only be changed internally through an approved public method, like a deposit function. Boom, your code is safe from tampering. Section 3, Pillar 2, Inheritance. Inheritance in code works a lot like it does in life. Just like you might inherit blue eyes or a specific height from your parents, in Python, a child class can inherit traits from a parent class. Imagine you've got a base class called Vehicle, and it already knows how to steer and brake. Now, if you want to create a new class called Electric Vehicle, you absolutely do not rewrite all that steering and braking code. You just inherit from Vehicle, and then you add the new specific stuff, like a battery level. It fundamentally saves you from writing so much redundant code. Section 4, Polymorphism and Abstraction. Let's break down the word polymorphism real quick. Poly means many, and morph means forms. Put it together, and it's simply the ability of a single function name to exhibit more than one behavior, depending entirely on the context. But I know beginners often get tripped up on exactly how this looks in practice. There are two main flavors you really need to know. First up is method overriding. This happens in a parent-to-child relationship. Say a parent-animal class has a make-sound method. The child-dog class overrides it to specifically say woof, while a cat class overrides it to say meow. Same exact method name, totally different behaviors based on the object. The second flavor is method overloading. Now, languages like Java let you write multiple separate functions with the exact same name. But in Python, we achieve this by making a single method adaptable. We use default arguments, or star args. So a single add function can effortlessly adapt to some either 2 numbers or 3 numbers. Same name, highly adaptable behavior. And that brings us to abstraction. Think of your TV remote. You press a button and the channel changes. What a relief that you don't need to actually understand the microchips, the infrared signals, or the internal circuitry to watch TV, right? Abstraction in Python is exactly that. We build all this complex background logic into our classes, but we only expose simple, easy-to-use methods to the user. We hide the messy details, making absolutely sure the user only interacts with what is strictly necessary. Section 5, Building the High-Low Game. Let's actually put this to work. First things first, we need a blueprint for our player. Notice how we're applying exactly what we just learned. The player's name and age, those are public variables. Anyone can see them. But look at the score variable. It has those double underscores. We've successfully encapsulated it. The player cannot just hack the game by manually typing score equals 100. The only way that private score changes is if the system itself calls the internal update score method.
Next up, we structure the game class. The number of rounds is public, established right when the game starts. But the attempts tracker? Completely private. This specifically prevents the player from cheating the loop by, say, resetting their attempt count halfway through. All the complex looping logic is hidden safely inside the play_game method. This is abstraction in action. The user literally just calls play_game, and all the heavy lifting happens behind the scenes. Let's quickly walk through the core gameplay loop to see our newly minted objects interact. Step 1, the system generates random numbers for both the computer and the player. Step 2, the user inputs their guess. Is my number higher or lower? Step 3, our game object evaluates that logic. And finally, Step 4, if the player is right, the game object communicates directly with the player object to safely update that encapsulated score. It is clean, it's secure, and it's incredibly organized.
And honestly, this is the ultimate payoff. Transitioning from basic functional programming to a solid object-oriented architecture means your code is no longer just a top-to-bottom script of rigid instructions. Instead, it becomes this interactive ecosystem of objects that perfectly mirror real-world entities. It makes your code highly scalable, incredibly easy to debug, and most importantly, endlessly reusable. You now understand how to protect your data with encapsulation, reuse code with inheritance, create flexible functions with polymorphism, and hide all that underlying complexity with abstraction. So I'll leave you with this one thought. Now that you finally have the blueprints to model the real world right inside your computer, what are you going to build next? Open up your IDE, create that first class, and just start building. Thanks for joining me on this explainer, and happy coding.